Good morning to all of you. Myself, Mr. Ahmad Shaikh, Assistant Professor, Sri Vasantrao Naik Mahavidyalaya, Dharani. Here I am presenting the aspects of pericyclic reactions. In this pericyclic reaction, we will see in brief the classification of pericyclic reaction, the types of reactions, FMO theory, cycloaddition reactions, sigmatropic rearrangement reactions, and there are some examples with references. First, the pericyclic reactions. The pericyclic reactions, any concerted reaction in which the bonds are formed or broken in a cyclic transition state, means electron move in a cyclic manner. That is, there is a single transition state from start to finish. It contrasts to stepwise reactions. Means, likewise, the SN2 reaction, this reaction takes place in a single step. That's why there is no intermediate. In a multiple synthesis reaction, there are the various steps with the intermediate, but the benefit of this reaction is that it gives the only one transition state, means the reactant directly gives the product without any intermediate. So this reaction is known as the atom economy reactions. The pericyclic reactivity can be understood in terms of frontier molecular orbital theory. It is known as the FMO theory, and the outcome of this reaction can be predicted using the Woodward-Hoffmann rules. Pericyclic reactions require light or heat and are completely stereospecific. That is, the stereospecific means the only single isomer is produced where there is a possibility of the racemic mixtures. That's why the reaction is known as the stereospecific in nature. The properties of pericyclic reactions. If any solvent effect, no nucleophiles or electrophiles involved, not generally catalyzed by Lewis acids. In some cases, there is a use of catalyst also, highly stereospecific, often photochemically promoted or by also heat. The classification, it's a simple classification for the pericyclic reaction. The first, the cycloaddition reaction. The second was the electrocyclic ring closing and ring opening reactions. Third one, the sigmatropic rearrangements. Fourth one, cheirotropic, and the fifth one, group transfer reactions. In cycloaddition reaction is a pericyclic chemical reaction in which two or more unsaturated molecules or parts of the same molecules combine with the formation of a cyclic adduct in which there is a net reduction of the bond multiplicity. The resulting reaction is a cyclization reaction designated as A plus B. A and B refers to a number of atoms containing pi electrons. Three important classes of cycloaddition reactions. One, the Diels-Alder reaction. The second one is a 2 plus 2 cycloaddition reaction. Third one, the 1,3 dipolar cycloaddition reaction. The first one, we will see the Diels-Alder reaction. It is discovered by the Professor Otto Diels and his student Scott Alder in 1928 and received Nobel Prize in 1950. Reaction between a conjugated diene and the dienophile. It is known as the Diels-Alder reaction. Highly effective method for the formation of cyclohexene ring. Means there are formation of two CC bonds in which the diene means the 1,3 dienes are used, and the second one is a dienophile, which is known as a simple alkene. They are reacted together in presence of heat or light, then it gives the cycloalkenes, which is the nucleus of this product. The diene must be is in the cis form, then it gives the product like that. And the dienophiles with electron withdrawing groups react faster. Here are the examples of these. In the first example, there is a 1,3-butadiene reacts with the propylene. It gives the product the cyclohexene, substituted cyclohexene. In the second example, where is the dienophile is with the electron withdrawing group, which is the ester one, and it gives the product also here. In a third case, there is a 1,3-butadiene reacts with the diene having the two electron withdrawing groups. It again gives the product. Here from the trend, we can see that The first reaction is slow, the second one is the faster, and again the last one is the faster. Means the rate of the reaction increases from first to the third reaction. It is because of why the this dinophile is having with the electron withdrawing groups. Therefore, we conclude that this reaction, in these reactions, if the electron withdrawing groups are present in the dinophile, the rate of reaction is the faster. We will see now the FMO theory. The cycloaddition can be explained using frontier molecular orbital theory. Frontier molecular orbital theory was developed in the 1960s by Kenichi Fukui, who recognized that the chemical reactivity can often be explained in terms of interacting highest occupied molecular orbitals and the lowest unoccupied molecular orbitals, means HOMO and LUMO. If the gap between the HOMO and LUMO is a smaller one, lesser one, then the reaction is a very faster one and unfavorable also. The alkene's dinophile compound has two electrons in a single pi bond. The FMO theory here identifies the HOMO and LUMO compounds of the system. The energy here in this diagram, see the psi1 and psi2, these are the orbitals belongs to the dinophile. The lower orbital is known as the highest occupied molecular orbital, means it contains the two electron. It is occupied, so it is known as the HOMO, is highest in energy, and another orbital which is anti-psi2, the lowest unoccupied molecular orbital, means is unoccupied, means doesn't contain any electron. Likewise, the dinophile, which has a 4 electrons is a conjugated pi system, can have its HOMO and LUMO identified within the FMO theory. Likewise, in the diagram, there are 4 wave functions that are the psi1, psi2, psi3, psi4. And in this diagram, it is shown that the psi1 is the lowest in energy and the highly stable. Then again, psi2 is a higher energy, psi3 is again higher energy, and psi4 again is a higher energy. Among these 4, these 2 are bonding orbitals and remaining 2 are anti-bonding orbitals. The lower, which contain the electrons, are known as the bonding orbital, and again upper 2, which are higher in energy, which are unoccupied, they are known as the anti-bonding orbitals. Among these bonding orbitals, the higher in energy, that is the psi2, it is known as the highest occupied molecular orbital, or simply it is known as HOMO. In unoccupied orbital, there are 2 orbitals, psi3 and psi4. Among these, psi3 is a lower in energy, which is unoccupied also, so it is known as the LUMO, lower unoccupied molecular orbital. If I examine the phases at the ends of the diene and dinophile, we find that the LUMO-HOMO interactions are phase matched. In this diagram, it is shown that the phase matching of the diene, HOMO of diene and LUMO of dinophile, or LUMO of dinophile or HOMO of diene. In the FMO diagram above, the size or coefficients are all the same, but usually they are of different sizes. The rules is that the coefficient match as well, small with the small and large with the large. There are regioselectivity. The cyclodation is always regioselective in nature. Next one, the 2 plus 2 cycloaddition reaction. The 2 plus 2 photo cycloaddition is a cycloaddition type reaction. In general, entails formation of new molecules by the reaction of 2 unsaturated molecules via 2 atoms from each molecule, hence 2 plus 2. In these, the cyclohexenone, under a photochemical condition, it gives the singlet of the cyclohexenone, then again is converted into triplet, and it is reacted with the alkene. Here is a triplet of cyclohexenone and the dinophile is alkene. They form the triplet exciplex complex. Then it gives the triplet diradical, and this diradical, first of all, they are showing the same spin of the electron, but after that there is a change in the spin, that is the singlet diradical is formed. And finally 2 plus 2 addition gives the cyclobutadiene product. The next one, the 1,3-dipole cycloaddition reaction. Here is the N oxides are reacted with the dinophile alkene with undergoes the 1,3-dipolar cycloaddition reaction and gives the heterocyclic compounds. There are 3 and 4 electron line which are react with dienophile, and from the 5-member ring, this is called the 1,3-dipole, and the cycloaddition reaction called as the 1,3-dipolar cycloaddition reaction. The sigma-tropic rearrangement reaction. Molecular rearrangements in which the sigma bonds or groups flanked by one or more pi electron system shifts to a new location with the corresponding rearrangements of the pi bonds are called sigma-tropic rearrangements. The total number of sigma bonds and pi bonds remain unchanged. Different types of sigma-tropic rearrangement reactions are 3,3 sigma-tropic rearrangement reaction, 2,3 sigma-tropic rearrangement reaction, 1,5 sigma-tropic rearrangement reaction, 1,7 sigma-tropic rearrangement reactions. Here, the 3,3 sigma-tropic rearrangement reaction. Claisen rearrangement or 3,3 sigma-tropic rearrangement. It is here the ethers of aromatic ring and also alkene is heated when this alkene fragment which is attached to the oxygen in the ether is migrated from oxygen to ortho position of the ring. This is the example of 3,3 sigma-tropic rearrangement reaction. This is a one-step rearrangement without ionic intermediate or any charge, similar like a cycloaddition reaction. Here the numbers are given from the saturated carbon, that is a 1, this is alkene 2, and this is 3. Then again from the oxygen the 1, 2 and ortho position acquires the 3. That's why the name reaction is 3,3 sigma-tropic rearrangement reaction. Again the 2,3 sigma-tropic rearrangement reaction. In this reaction, here are there is a it is an intramolecular reaction in which the alkene is also present and S sulfoxide which react together in a circular manner, and it gives a 5-member rings which contain the sulfur and oxygen which are heterocycles. In place of that, another reaction also which N oxide, cyanides, again other intermediates are also used to in this 2,3 sigma-tropic rearrangement reaction. Here 1,5 and 1,5, 1,7 sigma-tropic rearrangement reaction. It is in this substrate when it is subjected to heat, it gives the 1,5 shift, means the hydrogen which is present at the first position is shifted to the 5th position. Again, here is a in 1,7 the hydrogen from the first position is shifted to the conjugated system of the 7th position. That's why their names is a 1,5 shift and 1,7 shift. The electrocyclic reaction. In this electrocyclic reaction is a reversible reaction that involves ring closure of a conjugated polyenes for cycloalkene, or ring opening of a cycloalkene to a conjugated polyene. For example, a ring closure of 1,3,5 hexatriene forms 1,3-cyclohexadiene, a product with more sigma bonds and one fewer pi bonds than the reactant. A ring opening of the cyclobutadiene forms 1,3-butadiene, product with fewer sigma bonds and one more pi bond than the reactant. Here, the reacting ends of the pi system, that is Psi3 triene HOMO when process is a thermal. Here is the orientation of these orbitals, orientation of this HOMO. Here the last two orbitals which are the positive lobe on the upper face of the system, they rotate in a disrotatory manner and ring closure reaction takes place. Here is this example. Now we get the cis product. And the rotation is a disrotation, means one orbital in a clockwise direction and the another end in the anti-clockwise directions. These are the example synthesis of citral. In this synthesis of citral, here in the first step, 3,3 sigma-tropic rearrangement reaction takes place. Again, after this rotation, again it gives the 3,3 sigma-tropic rearrangement reaction, and we get the citral molecule. Fischer-Indel synthesis. In this, the hydrazine cyclohexanone condenses together, and we get this adduct, and finally it undergoes the 3,3 sigma-tropic rearrangement reaction and undergoes the intramolecular cyclization. And finally, in final step, we get the indoles or substitute indoles. Then dimerization of thymine residue of DNA. Here 2 plus 2 addition reaction or cycloaddition reaction takes place and we get this type of adduct. Then oxidation of alcohol. It is the one of the traditional method of the oxidation of alcohol by using chromium trioxide. Here is also 3D sigmatropic rearrangement reaction takes place. In this synthesis of stone, here is a one step, that is a 4 plus 2 means this other type of reaction. And in here is a Diels-Alder reaction. There is a 4 plus 2. This is a di and it is a dienophile which combines together. It gives the cyclic ether. And these are the references. Thank you.